So in this video, I would like to give you guys 8 examples of showing the limit of a multivariable function does not exist. And in order for us to do so, we will find two paths so that the limits along those two paths are different. Then we will be done. And just to tell you guys first, all the limits, they will be in indeterminate form. For example, for the first one, if you plug in 0, 0 into x and y, you end up with 0 over 0. So we have to do more work. And of course, in this video, all the limits are non-existent, but you will have to see how to write it out correctly. Anyway though, starting with the first one. X, y is approaching 0, 0, and we have x squared plus y over x minus 2y. Here, let's take a look at a quick picture. The origin is right here, and we have infinitely many different paths to approach the origin. I will first recommend you guys to do some easy ones. The x-axis is an easy one, and the equation for the x-axis is y equals 0. So we first say along the path y is equal to 0, and when we put this down, we can plug in 0 into the y right away. So we just have the limit. Now it's just looking at x approaching 0 because y is equal to 0 right here, and here we have x squared plus 0 over x minus 2 times 0. And here we just have a single variable case. The zeros don't matter, so we are just looking at the limit as x approaching 0 of x squared over x. And of course we can cancel this and one of this, so it's just a limit as x approaching 0 of x. And the answer for this is just 0. And keep in mind though, this is just a limit for the path y is equal to 0. Now we have to get another one. And you might be wondering, here we have x minus 2y. Well, if you put this equal to 0, that's just an equation of a line. Can we do that? I will tell you, no. Because when you are looking at this right here, you have to worry about the domain. Here, some of the limit equations will indicate that x minus 2y cannot be equal to 0. So this path is not allowed. Right? This is actually just an equation of a line, right? But it's not in the domain of the function, so do not choose that. But it's okay. Earlier we chose y is equal to 0. Now, why don't we try x equal to 0? Namely the y-axis. So let's try it along x equal to 0. This time we'll plug in 0 into x right away. So we get the limit as y approaching 0 of 0 squared plus y over 0 minus 2y. Alright, they don't matter. We are just looking at the limit as y approaching 0, and this is y over 2y. And you know it, y and y cancel. Oh, by the way, it's negative. But here though, we end up with what? It's just 1 over negative 2. When y is approaching 0, doesn't matter. It's just 1 over negative 2. So let me write it as negative 1/2. So along this path, we end up with this limit, which is of course different than that. So now we can just indicate that these two are not equal. Right? These two limits are different. You can also put like a non-equal sign here. Depends on how you want to indicate that. And once you have this, you can come back here and say this limit does not exist. Next, we have x, y approaching 0, 0, and here we have the absolute value of x raised to the absolute value of y's power. So if you plug in 0, 0 into x and y, you get 0 to the 0's power, which is indeterminate form. The result for this is now 1, alright? And the reason for the absolute value is because when x is approaching 0, for example, sometimes it can be negative. And when you have a negative base raised to some fractional power, you may end up with imaginary result. So we don't want that. That's why we have the absolute value for this. So what can we do though? Well, why don't we try to do what we did earlier? So start with along y is equal to 0. So this will give us the limit as x approaching 0, and then we are looking at the absolute value of x raised to the absolute value of zero's power. And it's just a one-dimensional case, right? One single variable case. To figure this out though, I think the easiest way is to look at a picture. So when we have x to a zero's power, this right here is just always going to give us 1, except for when x is equal to 0, so it's like this. And now x can be negative. So for example, if you have, let's say, -2 or -1/2, whatever, raised to the zero's power, the output is still equal to 1. And the reason I have an open circle here is because 0 to the zero's power, nobody agrees on what it is, right, as a value. So that's why I would just put an open circle for that. So for this case here though, we can see that the limit as x approaching, this is the x-axis, as x approaching 0, the limit is equal to 1. So it's like what we did back in Calc 1. Now, try the other path. Along x is equal to 0. Then in that case, we're looking at the limit as y approaching 0 of absolute value of 0 raised to the absolute value of y's power. Now, the base is 0 to a positive power. So if you look at the graph for this, technically for this right here, we are looking at the graph where this is the y-axis and this is just the output. If the base is 0, it's just always going to be like 0 right here. Just imagine you have 0 to the like third power or 0 to the 1/2 power. It's always going to be 0. Likewise, all 0. But again, if you have 0 here and 0 here, you know, it's big disagreement. I think that will be the best answer I can tell you. It's people will say it's 1, people will say it's undefined. No. Yeah. Anyway though, the picture will look like this. I am in the y world, that's why I put the y-axis here. And this is just the output. But the key right here is, what's the limit for this though? The answer for this is 0. So as you can see, these two are different. So once again, you can come here and say, this original limit does not exist. Now for the third one, we still have xy approaching the origin, but here we have e to the x minus cosine of y over x minus y. And if you take a look at the denominator here, you have to keep in mind that we cannot choose the path x minus y is equal to 0. Cannot do that because that path is not in the domain of this function. But it's okay though, let's just try what we did earlier. Again, just try the easy path first. Along y equals 0 first. Plugging 0 into y here and also y here, then we're looking at the limit as just x approaching 0, and then we have e to the x minus cosine of 0, and then x minus 0. Cosine of 0 is 1. So this right here is the limit as x approaching 0 of e to the x minus 1 over x. Now, if you put 0 into the x here and x here, you get 0 over 0. And some people say, just use L'Hopital's rule. Yes, but technically, this expression represents the derivative of e to the x at x equal to 0. So, I would like to just tell you that I'm not going to write down L'Hopital's rule because it's like, no. So, and I think in Calc 3, if you just go from here to the answer, which is 1, I think it's okay, all right? But I will still write this down for you guys. This limit represents f prime of 0, where the function is f of x, where the function is e to the x. And then if you differentiate this one time, you get e to the x, and then plug in 0, you get e to the 0, which is 1. So this right here is equal to 1. All right? Now let's try the other path. Again, the easy one. Let's try along x equal to 0. Okay, then we have the limit as y approaching 0 of e to the 0 minus cosine of y over 0 minus y. Now, this is the limit as y approaching 0. This is 1, and then minus cosine of y over this right here is negative y. So what can we do? Check this out. I'm going to bring this negative up here. So this is the limit as y approaching 0 of negative 1 minus cosine of y over y. Why am I doing this? Well, because it's pretty much the same idea like that. And I will tell you this right here is the limit as y approaching 0 of distribute the negative, but I'll put this down first, which is cosine of y, and then minus 1, and then over y. This expression, I'll just tell you guys. Okay, right here. This represents f prime of 0. And of course, this f and that f are different, where the function is cosine. Well, technically I should use y because over there we have y. Doesn't matter that much though. All right, and then if you differentiate this real quick, the derivative of cosine is negative sine y, and then plug in 0, then you get negative sine of 0, which in here you get 0. Therefore, this limit here is actually equal to 0. And again, in my opinion, if you just go from here to here without doing this, or if you're just secretly using L'Hopital's rule, I think it's okay. But the key right here is that this limit and that limit are different. So you can say they are not equal here. And you can come back here and say this does not exist. And then we are done. Alright, by now, you might be thinking, do we just always use y is equal to 0 and x is equal to 0 and then show the limits are different? No, no, no. Unfortunately, things will get trickier. For example, this one right here. X, y is approaching 0, 0, and then we have this expression. If you plug in 0, 0, you get 0 over 0. So we have to do more work. Let's just try what we did earlier. First, let's go along y is equal to 0. In this case, we plug in 0 into the y first. So we get the limit as x approaching 0 of x squared. That stays, but the y is now 0 over x to the 4th power plus the y right now is 0, and then we raise that to the 2nd power. Here, keep this in mind. Once we plug in y is equal to 0 into here and here, we have to do this limit inside out. So let me just write down this right here. And then we're focusing on just that. Here we have x squared times 0, which is just equal to 0, over x to the 4th power. So by looking at the inside, this is just going to give us 0. Now, the limit as x approaching 0 of 0 is equal to 0. Okay, nothing wrong with that. The limit for this right here is just 0. And let's try to go along with the other path that we like, right? X is equal to 0. In this case, we are looking at the limit as y approaching 0 of, here we have x is now 0, so we square that, and then we have the y over x is 0, and then raise that to the 4th power plus y. Okay, similar situation, and now check this out. 0 squared 0 times y, this is 0 on the top, over y, well, technically a square. But the whole thing inside is 0. So we are looking at the limit as y approaching 0 of 0, which is also equal to 0. So does this mean that the limit right here is equal to 0 because we get 0 and 0? No, no, no. Because in order for the limit to exist, we have to make sure the limit along all the paths are equal. But there are infinitely many different paths. We only have checked 2 of them. So you need to check out my other video to see how to evaluate the limit of a multivariable function. We have 5-6 methods in that video. But this video is all about showing the limit does not exist. So right here, if the limits are equal, we can actually argue that this limit does not exist. We just have to try to find a different path. Here's a tip for you guys. Have a look. Here we have x squared. Here we have y. Here we have x to the fourth power. Here we have y to the second. I want to think about y to some power so that the powers will match. Sometimes it helps. And have a look though. Remember, we are trying to approach the origin 0, 0. We have checked y is equal to 0, which is the x-axis, and also x equal to 0, which is the y-axis. Now, let's think about other ways so we can get to 0. One of the ways that you should also try is y equals x to some power. And I'm not going to try y is equal to x. This is also a path. It's along the diagonal like this. But if you plug that in, you can check it, but I'll tell you it's not so useful. Right? I'll actually do it for you real quick. So that will give us x to the second times x over x to the fourth plus x to the second. So we get x to the third over x to the fourth plus x squared. We can factor on x squared on the bottom. And then we can cancel. And then remember here, we have x is approaching 0. So this is x over x squared plus 1. As x approaching 0, this goes to 0. So it's the same thing. So don't do this. But as what I told you guys earlier, try to match the power so that some simplification will happen. So here, let's try x to the second power. When we have y is equal to x to the second power, we have a parabola, and you see that it does approach 0, right? So I am going to have the limit as x approaching 0, and then this x squared stays, but we plug in x squared into this y here, over x to the fourth power plus plugging this into the y, so x squared and then squared. Now this is the limit as x approaching 0. The top is what? X to the fourth power. The bottom is what? Here we have x to the fourth power plus another x to the fourth power, so we have 2 of the x to the fourth power. And as you can see in this case though, this and that cancel out nicely. Again, you work this inside out. Then you look at the limit as x approaching 0 of 1/2. It's just 1/2. So as you can see, this gives us 1/2. So along this path, this limit is different than that limit. So you can just say this limit and that limit are different. Therefore, we can come here and say this limit right here does not exist. And then we're done. All right, now let's try this one. The limit as xy approaching 0, 0. And by now you might be wondering, do we always have the limit as xy going to 0, 0? The answer for that is no, but this is just a very common case. I will give you guys xy approaching a different number later on though. But let's just try along y equals 0 and do the usual business. So this will give us the limit as x approaching 0 of x stays, but y is now 0 over x plus y is now 0. This whole thing inside is 0. So we get the limit as x approaching 0 of 0, which is 0. Okay, try the other one. Along x is equal to 0. Put 0 into here and here, so we get the limit as y going to 0 of 0 for x times y over 0 plus y. And you know what's happening, huh? This times this is 0, over y is 0. So this is the limit as y approaching 0 of 0. So this is 0. Bad, right? Well, I shouldn't say bad because we didn't do anything wrong, but it's just we cannot use this to draw conclusion. So what do we do? In fact, have a look. This is x to the first, this is y to the first. they already have the same exponent. So maybe we can try this when y is equal to x. In that case, put the x here. So we get x times x over x plus x. The top is x squared, the bottom is 2x. Reduce, we get x over 2. As x goes to 0, this thing goes to 0, so it's not helpful. So what do we do? X squared, like what we did earlier, let's try. Y equals x squared, put it there, we get x times x squared over x plus x squared. The top is x to the third power, the bottom is just that, but we can factor on x. We can cancel, so that's x squared over 1 plus x. When x goes to 0, 0 over 1. So this right here does not help. So what do we do? Here, check this out. Let's try to pick y so that we can get rid of this x and then somehow produce something that can simplify it with the top. And again, you just have to make sure you pick y is equal to whatever, so that this path contains the point 0, 0. So in fact, you can also say y is equal to sine of x, but don't do that. It's too complicated. You don't have to do that. But anyway though, let's try. I want to get rid of this x. So I want to have y is equal to negative x. How's that? Good, huh? And let's combine with what we did earlier, which is the x squared. So I'm just going to add a little bit. And the idea behind this is that this can help us get rid of the bottom and the x squared. You will see that because once we have the x and also multiply with this and that, you will see good things will happen and the simplification will happen. And keep in mind, when x is 0, this equation does contain 0, 0, so this is a legitimate path. Now let's actually just put this in action, and we have x right here stays, but the y is this, negative x plus x squared over x plus negative x plus x squared. Have a look. This x and that x cancel, and on the bottom we have x squared, and here is the limit as x approaching 0. Distribute the x on the top, we get negative x squared, and then plus x to the third power over x squared. So you see that we have the same power on the bottom, and this right here, in fact, it's a bigger power than this. So we have a very nice simplification. Why? Because now I can factor out an x squared. This is the limit as x approaching 0. Factoring out x squared, we get negative 1 plus x over x squared. Of course, you could have factored out x from here as well, but I did this. Yeah, doesn't matter. Now, x squared and x squared cancel. Yeah? Plugging 0 into here, you will see this is just negative 1 plus 0. So the limit for this is negative 1. Along this path, we have a different limit than this right here. So you can say this and that are different. Then we can come here and say this limit does not exist. Now for number 6, we finally have an example so that xy is not approaching the origin anymore. Here, xy is approaching 1, 1. So in fact, we cannot use x equal to 0, y equal to 0. No. Let's take a look at a quick picture. Let's say here is the point 1, 1. We have to think about a path that contains this point. Let's keep it easy. Let's try y is equal to x. Right, that's pretty good. So let's try that. First, we say along y is equal to x. So I will plug in x into this y and this y. So here we have the limit as x approaching 1. And then we have square root of x plus square root of y, which is now x. And then minus 2 over x plus y, which is now x. And then minus 2. Now let's simplify this a little bit. This is the limit as x approaching 1. That's just 2 square root of x minus 2 over 2x minus 2. Now, factor stuff up, right? This right here is 2 parentheses square root of x minus 1. Factor out 2 and then x minus 1. And in fact, not only we can cancel out 2, we can continue factor this. Let me show you. X minus 1 can be factored as square root of x minus 1 times square root of x plus 1. Well, you can do it the traditional way, multiply the top and bottom by its conjugate, which is square root of x plus 1, and I'll leave that to you. Now you see this and that cancel, and that's the key. Here, if you plug in 1 into here, we just have 1 on the top over square root of 1 plus 1. So all in all, we get 1 over 2. All right, so that's good. But now, what other path can we do though? We have tried y is equal to x. Maybe you can try the parabola that we used earlier, like this. Yeah, so if you say along y is equal to x squared, in this case though, we will get the limit as x approaching 1 of square root of x plus square root of x squared minus 2 over x plus x squared minus 2. And I will have to unfortunately tell you, this right here is also equal to 1/2. And I'm going to leave this to you guys to work out all the algebra and all that stuff, where you can check out Wolfgang alpha right here. Trust Wolfgang alpha for this one right here. Huh? So this right here actually does not help, unfortunately. Now, we have to find different path. And this is where it gets hard, because we have infinitely many paths. And if I didn't tell you in the beginning of the video, maybe we'll try to show that this limit actually exists to be 1/2. But the truth is, it's not. This right here still, it's a non-existent example. So what can we do? Maybe x to the third power? No. In fact, if you want to try y equals x to some positive power p, I think none of them will work. So why don't we try negative powers? So how about let's try y is equal to x to a negative 1. This path will still contain 1, 1. When x is 1, y is 1. So it's this right here, y is equal to 1 over x. Let's try that, right? Different power. So here, along y is equal to x to a negative 1, which is 1 over x. Here we get the limit as x approaching 1 of square root of x plus square root of 1 over x, and then minus 2 over x plus 1 over x, and then minus 2. How do we take care of this though? I will tell you, just do the conjugate. It works very nicely. So here, I'm going to look at this as the first term minus the second. I will multiply the top and the bottom by this right here stays. But I will change the minus to a plus. So I look at this as the conjugate, and then I will do the same thing on the bottom. All right, if you look at this right here as the first term, when you multiply the conjugate, we will get the following. This is the limit as x approaching 1. It's always going to be the first term squared, so we end up with parentheses square root of x plus square root of 1 over x, right? This thing squared, and then we subtract the second squared. And let me tell you the bottom, just keep it. So we still have x plus 1 over x minus 2, and then times square root of x plus square root of 1 over x plus 2. So let me work out the top for you guys. This plus that square, we first do this square, which is x, and then we add 2 times this term times this term, which in fact, this and that cancel because it's just square root of 1 over square root of x. And then we add 1 over x, right? Because that's the square of this. And then after that, we subtract 4. But notice this is plus 2, minus 2. Well, plus 2 minus 4, we get minus 2. So this becomes the limit as x approaching 1 of, the blue part is x plus 1 over x minus 2. 2 minus 4, that's how we get the minus 2. And we happen to have the same thing on the bottom right here. This now can be cancelled it with that. And finally, we are going to plug in 1 into here and here. So ladies and gentlemen, this is 1 over square root of 1 plus square root of 1 over 1, which is still 1, and then plus 2. 1 plus 1 is 2 plus 2 more. This limit is 1 over 4. So as you can see, this limit and that limit are different. That's why this right here does not exist. Now number 7. Once again, we have the xy approaching the origin. Here we have x sine x over sine y. Well, because we have xy approaching the origin, here you have to be careful though. In fact, because we have sine y on the bottom, we cannot just say y is equal to 0 because this path is not in the domain right here. The moment y is equal to 0, this thing right here is undefined. So we cannot say that it's a path that we use. But it's okay for us to say x is equal to 0. So start with along x equal to 0. Then we have the limit as y going to 0. Plugging 0 for x times sine of 0. And then over sine y. That's 0 over sine y, which is 0. So this is just the limit as y going to 0 of 0. So this is 0. Done. Now, next, we have to do what? Try this. If we have along y is equal to x, then we have sine x, then they cancel. Just x approaching 0, so that's 0. So how about let's try parabola, x squared. Yeah, let's try it. So here though, we are looking at the limit as x approaching 0. The top stays, but the bottom is sine of x squared. Now the question is, how do we work this out? Let me show you. I'm going to use one of the facts that I think everybody will agree on, right? I call this the limit, which says if today we have the limit as a variable, let's say theta, if it approaches 0, and here if we have sine theta over theta, this right here is equal to 1. And usually you can just quote this as a result, and in fact don't use L'Hopital's rule for this, and it's again like arguable, so I'm not going to get to that. I'll just say this is equal to 1. There's a geometry proof for that. You should try it. But anyway though, here I have x squared for the input. Let's have one more x here. So in order to do that, here let's say we have the x is approaching 0. Here we have sine of x squared, and then here we have x, and then sine x, right? I am going to multiply the top by x, but of course in the meantime, we will have to divide the bottom by x. So this and that still the same. Now I'm going to break them apart. This is the limit as x approaching 0. X times x is x squared. I'm going to divide that by sine of x squared right here. And then next we still have sine x over this x. Aha! X squared, you can do a quick substitution, say theta is equal to x squared, and because x is going to 0, theta will go to 0 as well. So this part is 1. Likewise, this part is also equal to 1. By the way, this is the reciprocal of this, which is still 1. So in fact, this is just going to be 1 times 1, which the limit is just equal to 1. So we're done. This is not equal, so does not exist. Now for the last one, we have x, y, and z. So this is the 3 variable situation, but the idea is the same. We have to find 2 different paths and we get 2 different limits and we will be done. Alright, this is approaching the origin. Let's take a look at the picture real quick. So x, y, and z approaching the origin here, and perhaps let's do an easy one. Yeah, let's say we want to get to the origin along the x-axis. But in this situation, we have to keep in mind that along the x-axis, y and z are both equal to 0. So right here, we will say along y is equal to 0 and also z is equal to 0. This is just to say the x-axis. Then we will just plug in 0, 0 into y and z here, and we will get the limit as x approaching 0, and then we have x times 0 squared times 0 squared, and then x cubed plus 0 to the 6 plus 0 to the 6. And remember, work this inside out. 0 times the top is just all 0, right? So this is just the limit as x approaching 0. The top is 0. This is 0, but we have x cubed. And then 0 divided by x cubed is 0. So this is the limit as x approaching 0 of 0. And the answer for this is 0. Yay! Now, we have to find another path. Earlier we used the x-axis, but if we want to try the y-axis, for example, that means x and z will be 0. But notice here, if x and z are equal to 0, then the whole thing will be 0. Same limit. That's not what we want. If you want to try with the z-axis, same thing, right? X times y squared will end up with 0 as well. So now what can we do? The answer is, when we have a 3 variable situation, well, sometimes maybe even more, like if you have to do that, try to use a parametric curve, like a parametric path. What that means is, we will write x, y, and z in terms of another variable such as t, and we have to make sure that the curve, the path, does approach the origin, right? So let me just write this down right here first. Along with, again, we have to write x equals, y equals, and z equals, right? Because you can think about it, if this is just 2 variables, we can say y is equal to some x. But if you have 3 variables like this, if you want to say y is equal to what? X and y, that's not a path, right? So x, y, and z in terms of t, but now what though? Here is the idea that we saw earlier, right, in the previous examples. Notice that here we have y to the 6, z to the 6, but this is what? X to the 3rd. Let's try to get the same exponent. And also notice y squared, y squared. So if you add the exponents, that's 4. If you imagine that we have some squares right here, that will be the 6th power as well. The 6th power on the top and the 6th power on the bottom will cancel off very nicely. So a good choice is x equals t squared, and then y just equal to t. Likewise, z is equal to t. And this is a parametric path that does go to 0, 0, 0 when t approaches 0. So that's the second path that we are going to use. And in this case, we'll just have the limit, but t approaching 0. And we will just have to plug in t squared into x. So here, t squared. And then y is t. And we have to square that. And then z is also t. And then here, t squared into x. So t squared, but that's to the 3rd power. And then plus y is t. And then that's to a 6th power. And likewise, z is also t. And then to the 6th power. Now just work this out. This is the limit as t approaching 0. The top is t squared, t squared, t squared, which is t to the 6th power. On the bottom is also t to the 6th power, t to the 6th power, t to the 6th power, 3t to the 6th power, just kidding. And now, I'm not kidding anymore, this and that cancel out very nicely, and the answer for this is just equal to 1, third. This is so good because we can see that they are not equal. Therefore, we can come here and say this limit does not exist. Alright, so hopefully this video helps you with your Calculus 3 class. Now, if you want to see how to evaluate multivariable limits, make sure to check out my other video, 6 methods that you should know.